Good morning, everybody. Glad to see everyone again. This is the second and last day of the workshop. What we'd like to do this morning is kind of pick up on and sort of keep a continuity going of where we started yesterday with some of the, of course, introductory components of platforms and sensors, the types of UAS analysis that we talked about in general terms, reconnaissance, surveillance, inspections, those types of things. Certainly the two-dimensional, three-dimensional mapping components. What we would like to do today is sort of focus in on taking some of these concepts and seeing how they can be applied to specific lessons and lesson plans that everyone might be laying out for middle schools, high schools, even two-year institutions and so forth. Obviously, everyone has their own interests, their own priorities, their own classes, certainly, on how they might wish to take this information and apply it. And that's where we want to go today. I'm going to try to keep this, again, as we tried to do yesterday, sort of informal. Certainly, we encourage through the chat room, or if you have a question and want to unmute and ask it, that's fine as well. We're here to obviously to answer any of those questions. We're going to start off this morning, Steve Sorensen and I, on lesson plans specifically, and lesson plan examples. And I'm going to talk a little bit this morning about the importance of maybe developing partnerships for research-focused projects, maybe that you could partner up with various maybe local units of government or state agencies. Certainly, if you have any 2- or 4-year institutions that are in and have the ability to work with drones and drone analysis and so forth, it's that inner working relationship, I think, that can make many of these lesson plans successful in terms of their development. So that's where we want to go this morning primarily. We'll try to break, well, we'll see how much we have this scheduled from 10 to 11:30. We may not go that long, but after the initial presentations this morning, prior to lunch, we'll sort of break out and I'll talk a little bit more about what we're going to be doing after lunch. If you were aware of that yesterday, we're going to sort of divide up, depends on the number of participants that we have here, but we would like to break up into small groups, and we're going to go into sort of virtual rooms where a facilitator like myself or Tom Biller or Steve Sorensen or Tom Oyne will sort of facilitate a discussion amongst the groups in these rooms. And hopefully what you'll do is to, in a very generic way, talk a little bit about how you might be able to incorporate UAS more fully into your curriculum. And perhaps also what we would like to do is to sort of, using a template, develop sort of a generic lesson plan. And then a little bit later, we'll sort of come out of those rooms, and we'll end up this afternoon then, you know, probably around 2 o'clock or so, sort of presenting these, sort of doing sort of a final wrap up on, again, what's feasible, what isn't, what some of the possibilities are. And again, at each step along the way, if you have any questions, and even, I don't know about some of the others, I would certainly be willing to stick around a little longer for individuals who might have specific questions for a specific course that they may have. And we'll just see how that goes. And like I said, then we'll have that general wrap up of a discussion of our finished lesson plan. So if that sounds all right to everybody, what I would like to do now, or what I'm going to do, is to share a screen that I have. I'm going to make two presentations, PowerPoint presentations this morning, discussing some of the practical applications and curriculum development that we have done here at St. Cloud State and up at Northland and so forth, and see how that goes. And again, sort of present these as examples, not necessarily, well, this is the way you have to do it, or this is a specific structure. Nothing like that. Just an example, a sort of a springboard into a greater discussion on curriculum development and how it can make use of unmanned aerial systems within that. So I'm going to share a screen, and there it is. So share. So is everybody with me? Do you, if I can get some feedback so I know I'm not talking to myself. Can you see the screen here? It should say partnerships.
Yep, it looks good, Ben.
Okay, all right. Well, again, the whole idea, as I indicated, was that obviously we all operate with, as we know today, with limited resources, maybe right now limited contacts, and the whole idea is that you aren't out there alone, that you might say to yourself, yeah, this really sounds like something I would like to put into my class, my social studies class, my techniques class, my engineering class, environmental, whatever it might be. But, you know, like anything else, where do I start? Like we talked about and Steve was mentioning yesterday, where are those sources of imagery that I might be able to tap into? Are there lesson plans that have already been developed? Are there templates that I can use? And that's really the purpose of this workshop. And again, to point out the possibilities that we're going to have as we developed the, or as the National Center for Autonomous Technologies, NCAT, develops and expands into a variety of areas, curriculum, of course, development, serving as a repository for lesson plans, for imagery, small data sets that can be shared and used with these, is where we see this going and how we see this development taking place over the next few years. But no, you're not alone. And if I think in your own, and you're probably aware of this as well, but I think in your own situations where you may have a county agency, a soil and water conservation district, your Department of Natural Resources, who's out there and maybe using drones, who has information, who has imagery, that they too would like to share. And you'd be surprised how many of them are interested in not only doing the research, but taking the results of that and sharing it, certainly with middle schools and high schools in terms of development. Hence the partnerships. So I'm going to, there we go. Now, I'm just putting this up as an example of what we've been doing here at St. Cloud State. Obviously, we too, even in the four-year institutions, are interested in developing partnerships with other research universities, other units of government, nonprofits, and so forth. So as you see here, and if you note the logos, I'm just going to let you look at this for a moment. There is something that's taking place at the University of Minnesota, who in themselves are working cooperatively and with what's called the Forever Green Initiative, and at the University of Minnesota, and also the Land Institute. And what this is all about, and again, you can see University of Minnesota, the initiative, Stearns County Soil and Water Conservation District, St. Cloud State University, and the Minnesota Association of Professional Soil Scientists, MAPS. These are, again, different professional societies, universities, county and state federal agencies and so forth, that have we are all working together on a project for Kernza. And if you're not familiar with that, and you're probably maybe not, I will do this. Kernza, this is kind of an interesting project, and it has a number of ramifications, again, with crop development and crop domestication, with certainly soil conservation, a variety of aspects, again, of things like soil erosion, protection of water and the water table. And one way of doing that, I think many researchers feel, is to try to keep crops on the ground throughout the year. And that's the idea of the aptly named Forever Green project, that instead of just growing annual crops, you know, beans, wheat, corn, that type of thing, that grow over a few months, you harvest them, and then the soil lays bare throughout the year, subject again to erosion, degradation, soil health degradation, and so forth, is very important these days. So Kernza, again, is, as it says, a perennial wheat grass. Actually, it is a wild grass that tends to be native to areas of Central Asia. But the thing about it is, it develops this tremendous root system, much more, and I'll show you an example here in a moment, extensive than wheat. And not having, as it says, to prepare the soil each year, along with that root system, means that Kernza can reduce soil erosion considerably, and it also fixes, very importantly, carbon in the plant and reduces the leaching of nitrogen from the soil. These are all very, very large problems that we have in trying to maintain, of course, not only the health of the soil, but the quality of our drinking water and so forth in terms of pollution. So again, anything that we can do, and again, this is a perennial wheatgrass. It should, you know, grow every year. The problem is, in its wild state, it has the certain problems, if you're familiar with this, of shattering in terms of the plant itself, the seed system. The seeds need to be developed. This is all part of the domestication project that is taking place down at the University of Minnesota. And they have, as we will see here, various test plots. This is the St. Paul campus down at the University of Minnesota in the Twin Cities area. You can see the St. Paul campus here in the background, but in the foreground, this is Kernza. And you can see, again, some of the seed harvesting and so forth that students are working on here. And that's all fine and good if you're growing this under controlled conditions for genetic studies and, like I said, plant domestications and so forth, and developing a seed product that is going to be economically viable to farmers to be able to produce. But these are small plots, and what the university wanted to do was to work with various county soil and water conservation districts on certain specified kinds of soils and in watershed protection areas to have farmers volunteer maybe some fields where the crop, again, that is being developed down there could be grown under just, you know, not controlled conditions as we see here, but sort of general farming, and to see if the crop that and the yields from this crop that are produced on some of these fields outside of the Twin Cities, especially in central Minnesota, has some type of capability of providing the farmer with some revenue. So they're also partnering with certain companies. I think General Mills would be one. They're interested in seeing that if, you know, can this Kernza be developed to the point where it can be milled for, you know, making bread and that type of thing. There are some local breweries that are interested in developing beers that could be made from Kernza grain. So this is a rather interesting project, as I indicated before, in which this domesticated perennial wheat grass hopefully may be able to develop to the point where it can be grown throughout extensive areas in the Great Plains and Upper Midwest and so forth. So from this, this is what we're talking about, and it's really quite amazing when you see that. Here you see over on the left, sort of a cross section. These are on some test plots. As I indicated, the Land Institute is down in Salina, Kansas, and they're the ones that sort of leading the way with this and other types of crops, again, that can support soil health, water protection, and that type of thing. Over here on the right, you see where I'm kind of pointing here. That's just a regular crop of wheat. Kernza is over here on the left, and I would point out to you, note the extensive root system that you have with Kernza that you don't get obviously here with the wheat. And if you go over to the right and see these here and here, this is the normal root system. These are two different dates of growth, the initial stages, somewhat of a more mature stage. But again, note the wheat as opposed to the Kernza, how deep, how dense that network system is of the roots. So this is really where they're trying to go with the domestication. They know what the potential is for developing Kernza over areas, again, of the upper Midwest especially, on some soils that, again, are probably prone to leaching. These would be very sandy kinds of soils. So I'm just, granted, this may not be the type of thing you might have a direct interest in, but where I'm going with this again is how different components can be brought together in a partnership, and how with that development and study, some of this could pass into the curriculum in environmental classes, in farm ag classes, in two-year tech schools, certainly in environmental studies classes in high schools and universities as well. So one of the areas that is being tested out of the Twin Cities, where we're actually going to get it into the hands of real farmers, is up here actually in an area in our county, Stearns County in central Minnesota. And just to the west of here, probably about 10, 15 miles, is the city of Cold Spring. And Cold Spring is situated, there are a lot of, because of the glaciation that took place in this area in the past, you get a lot of areas of sandy outwash from that old area of glaciation, very sandy soils. And these are soils that in which the water, because of the coarse nature of the sands, moves through rather rapidly. And of course, if you're not careful, of course, all the fertilizers, the nitrates, pesticides, and so forth that get spread in these soils can have the potential of leaching into the water table very quickly. And so several of the cities west of here, Avon, Albany, Cold Spring, as you see here, have developed what they call wellhead protection areas. And those are areas in which they're trying to develop farming practices, soil health and invigoration and so forth, to try to prevent this leaching. And that's why they're looking to see how this Kernza crop might really aid in that kind of development. So here's a friend of mine, Brad Wentz, who's with the Soil and Water Conservation District. Actually, this field that we see over here has several test wells in it, and you can see the actual wellhead here for the drinking water for Cold Spring. And the soils that you see out in here and so forth are those rather coarse textured sandy soils that perhaps Kernza could be used in as a perennial crop, not just the annuals. Again, this is a ground view This is one of the fields that we are studying. And when I say we, of course, I mean Soil and Water Conservation District, the University of Minnesota. We have sort of developed, as I indicated, a cooperative relationship. And what we bring to the table here is the fact, of course, that we have the ability to fly these fields with our UAVs fixed with, and we're just beginning to do that now. We were using Inspires, but now we have been able to obtain a much better UAS system, in which we, and as Greg Emmerich was talking about, we have the ability of using some of the Centera sensors and thermal sensors to fly these kerns of fields and hopefully come up and utilize aerial imagery that will help us to measure stages of growth, the health and vigor of the crop as well during different times of the year. So our idea is to do multiple flights throughout the year as the crop is coming out of senescence and, of course, beginning to develop from the harvest later in the year. You will note here again, I don't know how well you can see it, Tom Owen and I have been doing a couple of these, or several of these flights. You can see the drone right here in flight. There's that waterhead, and we're looking at the field right here. And again, note these, like I said, very sandy soils. You can even tell that by the irrigation here. So one field that we have specifically been looking at, and that was one that I showed you yesterday. Remember where we were doing that kind of circular view using one of those intelligent mode applications. But here's a field, and you can see it's rather different. It's made up of soils, like I said, that basically are rather sandy. You can also see, exaggerated as it is on this field, some of the areas that are not, you know, maybe as well drained. This is that a field of Kernza that you just saw. This was taken during one of our flights. Again, a lot of this is still experimental at this time. No one knows exactly how this is going to work. No one knows exactly what the final kind of plant structure is going to be as they begin to develop that. But at least we're trying to build a baseline of data of UAS flights in this area to help. And again, like I said, this is all in partnership. This is one of our earlier flights, soybeans over here, the more ripened Kernza. This is an August flight, and you can see the Inspire one that we were using at that time. And as you saw yesterday, and as Steve Sorensen was pointing out, and some of the work they were doing with ditches and so forth up at Deep River Falls in the Northland College area. Of course, what you're going to get when you do any flight is just these number of individual images with a very high overlap. Again, not going down that photogrammetry rabbit hole right now, but suffice it to say that, you know, when we're flying these and to get the proper, now we are flying without, at this point, any kind of ground control. But with the heavy overlap that we have of 80–85% and side lap and so forth, we can get some pretty good orthomosaics, decent orthomosaics, at least for our needs, out of this, as well as a height, and you can see the crop height here in terms of a digital surface model. So these are the kinds of data sets that we can develop that can be worked with and analyzed by Soil and Water, that can be studied by the researchers down at the University of Minnesota. Again, it's just one of those partnerships that works. Here's that orthomosaic superimposed over a Google Earth image, so you can kind of see what we're talking about here. And then again, Here we have draped that over, of course, the three-dimensional and perspective component that we get in Google Earth. Again, you can see that poorly drained area. The thing about Kernza, and you might look at it and say, but what, that didn't look very good. Well, initially they plant the rows about 15 inches apart. So the textural interpretive part looks rather crude in the early stages of growth. But I think, as Tom Moyne can attest as well, you know, you come back in a couple of weeks and those inter-row areas are really covered up, except there are these spots in here where, and I don't think they bothered to plant through them. These are weeds in poorly drained areas of the field. So there's a lot of variability, and of course we can pick that out on the drone imagery. This is a basic scouting or reconnaissance view I took with my Mavic 2 Pro zoom, and again you can see these areas. It just gives us that perspective for sort of a common view. And of course here, and I chose this just because of the extreme variability of some of the poor drained areas. These yellow high green areas are certain kinds of weeds in the field, and again, everything else, of course, you can see the bare soil, you can see the crop, obviously the Kernza. And as we're just going to zoom in here a bit, you really do begin to see the capabilities here of using drone imaging, where you have resolutions that are really down pixel sizes into the centimeter size. And again, not just for crop scouting, obviously, but actually almost phenotyping capabilities that we get. Yeah, where, you know, you're able to look actually at individual plants. And I'm not going to zoom down all that way, but I think you get the idea of yeah. Okay, there we go. This is a real enlargement. I really went in and just so you could see the kind of resolutions that we can get. You know, we pixelated to the point where we're looking at, of course, individual pixels in the field. Kernza is basically over here and on the sides. Most of what you see are those weeds. Remember that yellow mustard colored colors that you got, and I just did that to bring out the color variability. But I did actually, you know, we actually did a measurement. You can see that you know, this pixel is 1.4 centimeters on a side. And again, we were using, we have now, as we're going to fly, and I think, Tom, if you want to say anything about that, certainly sensors that have much better resolution even than what we have here.
And I would just add that in one of the pre-workshops, sometimes the flight height and getting down, and I think Kirk Stuvey yesterday's, the resolution as far as processing it with all the software, it's really down to a point that you don't need that 1.4 centimeters for a lot of it, because that processing on the VRA variable rate and a lot of that equipment is not down to that point yet where it can make a significant difference. So
yeah,
as we mentioned, we're typically flying between 200 and 300 feet for most of the flights, so you can get that so you can get those key points that we had discussed earlier, which I think are very important to doing that mosaic mapping. Otherwise, you won't get enough returns on some of these fields.
That's a good point. That's an excellent point. And you know, you also have to remember that as you, whoops, I'm just going to go the wrong way here. You know, whoops. You know, as you look at certainly some of this, that if you're looking at you know, somewhat larger areas of the field, you want to, in your basic scouting and so forth, want to see where you may be having troubles with your irrigator, where you may be having troubles with your pesticide and so forth. You don't need to get down to the individual plant to see where you have trouble. On the other hand, more and more, because we do have some of these fine resolution capabilities. And as Tom mentioned as well, of course, you know, being able to fly at different heights and so forth can make a big, obviously a big difference on your resolution. But for you know, phenotyping and that type of thing, where you're trying to see, and that's one of the things the University of Minnesota is interested in, especially with maybe some thermal imaging, is there any way of being able to break out just in terms of the moisture content and the heat signatures that you're getting from some crops, the moisture in the seed. And again, for individual phenotyping, that can be very important. Like I said, a lot of this is, as we know, sort of a experimental component. One of the things that we also did just as an experiment, and again, we weren't using a great thermal sensor, but at the same time, this is that same Kernza field flown with thermal. And again, it may not have the kind of resolution, but that we do, I think, have a thermal sensor now that will be better than this that we can use. But again, you can note here's the obviously the warmer areas versus the cooler areas. Again, bare soil, or as you can see along here, they came through and sort of cut along the shoulder of the road. This isn't really the Kernza, it's just more grass that they mowed, but it's dead. It doesn't contain the moisture content that would keep it in this daytime image cooler. You can see the road here, and you can see the sort of fractured look. Those are, of course, tar patches that they made on the road, and much more in this thermal image variable. So again, like I said, this and a couple of other test sites are what we have been flying up here. And as I indicated before, working cooperatively with the University of Minnesota Crop and Ag Department, with Soil and Water Conservation and the Forever Green Initiative, and MAPS, soil scientists who are also interested in this. Here's our elevation map. We have superimposed on top of it different soil types. And again, these soils have a rather sandy structure associated with them. Like we said, it's seen here. And this was part of our Minnesota Association of Professional Soil Scientists field tour that we took. It included a good discussion on the Wellhead protection site. Excuse me. And here's that field that we flew. And again, we used imagery to also educate these professional soil scientists and hydrologists on what the advantages are of not only Kernza, but being able to monitor it with UAS systems. Again, note the tar patches, and again, you can see the cut grass on the side that they've, so you can kind of see how that thermal image, you know, came into play there. Anybody have any questions on that before we, granted, it may be that, well, what do I care about a perennial wheatgrass? I understand that. It's the concept I'm trying to get across to you, that there are a lot of sources out there that, again, you might be able to partner with, or groups, like I said, agencies, various research institutions and the like. I think that you can find that would be very helpful in supplying with information, ideas for maybe a curriculum component that you may be able to use in one of your classes, not necessarily just wheatgrass, but you know, partnerships are very important, I think. Not only, you know, for high schools, but two-year institutions, universities like ourselves, and so forth. So yeah, it's really something to think about. and you may have ideas on your own about who you might want to approach.
So Ben, we do have a two-part question out there. The first was, what was
Two-part?
the, two-part. What was the AGL when you got the 1.4 centimeter pixel size? And then what resolution do you typically get at 200 to 300 feet AGL?
Well, again, you saw that, Tom, still there?
Yes,
Yeah.
Michael.
We were flying 200 feet, weren't we?
Well, it's going to be dependent on the sensor, but I'm responding to you right now in the DRONETECH in the flight overview PDF that's in one of the pre-workshop materials. There's a very nice, very easy chart that describes different flying heights and obviously the trade-offs with flight height and the GDP ground resolution. And accuracy, because as we've talked about, they're all very highly correlated between the two. So it's just kind of a trade-off. And the other factor is, and we all know it, is the battery life and what kind of area at what height can you actually fly and get a field flown and what makes sense. We can fly it at a much higher resolution, but at what point are we sacrificing how much, our battery life and what actually surface area we can fly. So in that slide deck, and I'm going to respond, it's in that, and it's kind of a nice overview because it does give a very good feeling of, okay, there's always going to be trade-offs and it really depends on what you need. And when you start processing it in Pix4D and the other software, it will tell you exactly what your GSD that Ben has been referring to as far as your pixel resolution is. It can attain a crazy high pixel resolution, but then you might have a trade-off as far as if you have too much conformity in your surface area and you can't get key points that Zach has talked about and that Ben's talked about, you might not be able to get those key points that are needed to get a mosaic, to get that geospatial product that you want. So I'm just finishing up and I will try to do an attachment, but it's I'm going to turn it back over to Ben.
Yeah, the other thing that you need to be thinking about as well as Tom indicated, the field that you just saw, excuse me, that we were flying, actually both of the fields that we flew around the Cold Spring area were around 17 to 18 acres. And I think we pretty much did it on one set of batteries, but it just depends. But that of course is one consideration. And the other thing that you probably need to keep in mind too, if you're flying multiple sensors, you try to come up with an optimum height. Now, obviously, you're trying to build in, especially with UAS, as much overlap as possible. I know that, as I talk to my students in class, and when we start out with the traditional photogrammetry and, digital aerial cameras that we're using for traditional photogrammetry, you work with something like 55 to, well, let's say 55 to 65% MLAP between what's covered on one photo to the next, and so forth along the flight line. And that's sort of standard. When you get into UAS, as you probably know, and especially if you're trying to come up with ortho, or to try to develop ortho mosaics, again, that will have a certain level of accuracy built in, especially if you're not going to be using ground control, then all of a sudden you're up to 80, 85, maybe even 90% overlap. So, these are all considerations that you have to make. This is why pre-flight planning, just, hey, let's grab a drone and go out and see what we can get. It really doesn't work if you're trying to do something like this in a some type of scientific study. But also to the point, you saw the simple RGB and thermal images that we flew on that field, that Kernza Field north and west of Cold Spring. That thermal is going to tend to be, just because of the very nature of thermal and the way we gather it, it's going to have coarser resolution than you're going to get with the RGB. And so if you're going to stick both on a drone platform, fly them all at the same time, you have to be thinking in the back of your mind, okay, the type of camera that I'm going to be using, the amount of overlap, how high am I going to be flying? All of these, of course, are going to have impacts on the scale of final imagery. So it's going to be kind of a trade-off, because chances are you may find that you're going to have to fly the optimum height for thermal might be a little bit different than the optimal height for RGB. So where's the trade-off there? It's going to affect the scales, obviously, and potentially the use for both. And again, remote sensing in general is sort of a trade-off in terms of what you want, what you're going to actually be able to get. And I think Tom addressed that issue pretty well. I don't know if that answered the question or not. But.
So Ben, on top of that, I just want to put out there that there are a couple of apps out there that are very good at calculating GSD,
Right.
and there's even one called Drone Dimensions that I know is available on the Android series. I don't know if it's an iOS, but it actually already preloads the most common cameras, mainly from DJI platforms.
Right.
And you can just select the camera. It tells you the GSD at a given height, and you can play with the information as far as height and stuff like that. There's also one for thermal. That one I think you have to pay for, but it's Drone Dimensions Pro, and it'll do the same thing with your thermal camera. So you can put in information like your spot size, so you can get your SSR and things like that. So there are plenty of tools out there that'll do it for you pretty well automatically.
That's a good point. Thanks, Zach. I appreciate that. Yeah. Is that the two-part question?
That was the two-part question, and then I'm scrolling back up here. I know Steve kind of addressed it a little bit, but Pete was saying that we could use this to track algae blooms that are very toxic, and also movement of nitrogen from farm and homes. Wondering if you ever did something like that with farms and rivers. I know there's been some folks out there that have done it, but have you guys specifically?
Not that specifically. What I'm going to be talking about next is an example of monitoring algae bloom in a lake. We have done nothing as of yet. Most of what we're doing at this time is simply monitoring the crop vigor, maybe chlorophyll production, canopy closure, things of that nature. We really haven't gotten to the dynamics yet of the hydrology of it and so forth. Again, I think these are all topics certainly that would be wide open for further study, which again, being able to bring these different levels of expertise together is why partnerships are indeed so important. Yeah.
Absolutely. Thanks, Ben.
Okay.
Looking in the chat, I don't see any other questions there. So if anybody has any, please feel free to speak up or type up.
Yeah, and certainly we can, even during lunchtime, if people want to stay on and talk about it more. Also, we might be able to talk about that in our breakout sessions after in the afternoon.